Yes. I have 45 minutes. So I want to say just a little bit about, it's probably hard to do many details, but I want to say a bit about the proof. So it's a comparison of trace formulas, specifically stabilization, stabilized trace formulas. So there's actually 4 formulas, and one is we could call the discrete part of the trace formula for G. And what it is, so there's 4 formulas. This is the first one. And it is the part, it's kind of the payoff for the trace formula. It is the part that you really want to understand. Everything else is supposed to be, at least from the point of view of what we're discussing in this topic, everything else is auxiliary to this thing. This is the thing you want to understand. The other parts of it are things you want to use to understand it. And so it's the part of the trace formula that is spectral and is discrete as a distribution in the spectral variables of a test function. And so it really amounts to a definition. The discrete part of the trace formula is the following explicit formula. It's a sum over Levy subgroups M, say taken up to conjugacy of the group G. This is the trace formula for G. Again, the coefficients are not terribly important for the general description, although they're important for when you have to compare these things. And so the coefficient is the determinant of an element in the Weil group, minus 1 to the minus 1. This is acting on the Lie algebra. It's a linear transformation. A regular element in the Weil group means it has no fixed vectors in the vector space that corresponds to the split component of the center of M on which W acts. And then the main term is a trace. And it is essentially, if M were equal to G, it would be the discrete spectrum of G. But there's some other terms indexed by arbitrary Levy subgroups. And they are the trace of an intertwining operator, MP of W, attached to this element in the Weil group, composed with an induced representation. And so it's an induced representation of a test function of f. So f is a function, again, in the Hecke algebra. This is the global. So here we're back to the case where f is global. I'm just going to say these things. I won't write them down. This is an induced representation from a parabolic subgroup. What is the induced representation? It's the discrete spectrum of the Levy component M, also taken modulo the split component of the center of M, so that there really is a discrete spectrum. And you induce that up to G. That's an induced representation. And then this is an intertwining operator of that induced representation attached to an element W in the Weil group. And that's a very interesting term. This is kind of what's left over. This is the reflection of Eisenstein series. They give the continuous spectrum, and that's not part of this term in the trace formula. But when you truncate it, there's a little, the Eisenstein series spill over, and they give a contribution to the discrete part of the trace formula. And it's the scattering matrix that gives the functional equation of Eisenstein series. So this is the payoff. This is what you want to understand. And really, it's just the term when M is equal to G, the discrete spectrum on G, that is the real term you want to understand. After all, we're trying to prove a decomposition about the discrete spectrum of G. This is what one wants. This is the term in the trace formula that gives it. It's got all these other terms here too, and they somehow cannot, in comparisons, they have to be taken into consideration too, because they don't match up quite like this in the things you're comparing them with. So I just say that this is part of the trace formula. Maybe it looks complicated if you're not familiar with it, but it is much less complicated than the complementary terms So this is really an identity. I'm defining it as this, but this is an identity between a bunch of other terms, orbital integrals and so on, that perhaps geometric terms, which are more complicated. But this is the thing that comes into the comparison. Secondly, is the stabilize. Question? Yes. What is psi? It's not supposed to be there. I was going to put that in later. This is, yeah, I'm sorry. Thanks. Secondly is the stabilized trace formula. For G. And so really, this is not a formula. This is kind of a definition. I'm calling it a formula, but it's really a definition. The next one really is a formula. It is another formula for IG discrete. And it is, this time, if this is kind of a spectral formula, a decomposition of a certain object, a certain distribution, this is an endoscopic decomposition of the same distribution. So this is a sum over, so I alluded to endoscopic data for the given group G. They can both be local and global, although they're closely related. I'm looking at actually endoscopic data which are so-called elliptic endoscopic data. And that means that this, as a group, that the split component of its center is the same as the split component of the center of this. In other words, it's not as small as a Levy component. It's almost as big as G. They're the things that come in. The elliptic endoscopic data are the ones that come into the stabilization of the trace formula. And it is a formula in which these are explicit coefficients that were first introduced by Langlands, and then Kottwitz gave a very simple formula for them. And then some unknown, it's very kind of on its own. It's really just quite a weak formula. A stable distribution on G prime evaluated at the transfer fg prime, which I mentioned locally last hour, of a function of this function f in h of g. I'm actually, at the risk of being confusing, this stands for, f stands for a function on the group. This stands for a function on the set of stable conjugacy classes in that group. Really products. This is an adelic group, so it's stable conjugacy classes in the adelic group. And I'm going to write S hat for the stable distribution. It's pulled back to a linear form on the space of test functions on stable conjugacy classes. OK, so in any case, it's a completely separate kind of decomposition of this rather explicit but moderately complicated formula, the one you want to understand. But it just says that there are stable distributions on all of the different endoscopic groups such that this equals this. So in some sense, this really also represents a definition. The elliptic endoscopic groups typically...
Isn't there another way to think of these I, the buckets, as sort of an inclusion-exclusion? Because you came through this...
No, they're more, they just got 2 or 3 terms. This is the order of the center of...
So they're all positive.
I guess, are they positive, Diana? I think they're all positive. I'd have to think about it for a moment. Don't have time to think here. I think so. They're all, but pardon me? Oh, thank you. Yes, yeah, okay. Positive, yes. Okay, so typically G is a product of 2 groups of the same form. G prime is a product of 2 groups of the same form as G, orthogonal, or groups whose dual groups are orthogonal or symplectic. One could assume inductively that one knows the definition of this thing for any composite group. And what's left is the case where it's not composite, where G prime equals G is also an endoscopic group. And so this kind of would really represent kind of a definition of the stable distribution on G in terms of things you know, namely it's inductively, it's values taken at products. So in some sense, it's almost like another definition. It's saying that it's saying something. It's saying that this complicated expression here and the term with G prime equal to G here, minus these things that you know, that it's actually stable rather than a more general invariant distribution. But that's not going to get you too far all by itself. So you've got those two formulas. If one tried to make the comparison of these things, well, if one tried to prove theorems just based on those formulas alone, one really wouldn't get too far. But fortunately, we're trying to classify representations of G in terms of representations of GLN. So there's another pair of formulas. This is so I'm going to call this 1 tilde. I'll call this 2. And then I'm going to say discrete part of twisted trace formula for GLN. And so that basically is a formula that's just like this, except rather than taking the trace of a test function on the discrete spectrum of G, one would think of it as a way to understand the trace, the twisted trace of the discrete spectrum, say, on GLN, or in other words, the composition of the test function f with the outer automorphism of GLN. And so, but it has more or less the same form. I'm going to write it as 1 tilde. It is, again, the first thing amounts to a definition. The discrete part, I'm going to write it as an upper n of f tilde. F tilde is a function on GL on the Hecke space of the global Hecke space of GLN. And it's almost the same. And I'm taking this as a definition, but it's really a part of a larger formula where there's another side that consists of more complicated geometric terms. And so this is a sum over Levy subgroups of GLN, again, with quotient of orders of Weyl groups. Now this is a Weyl group induced on the split component, on the center of, acting on the center of the split component of this Levy subgroup of GLN, but it's Weyl group elements that are induced from the non-connected component of this semi-direct product. So it's an interesting set of Weyl, it's a Weyl set, it's not really a group, it's a torsor, I guess. Yeah, it's a torsor under the Weyl group for GLN, but it's a different set. And again, it's regular elements in this Weyl set. And again, it's the determinant of W minus 1 to the minus 1 and absolute value to the minus 1. And it's the trace of MP, again, an intertwining operator attached to Eisenstein series, IP of F tilde. F tilde in H tilde of N. This, I guess, we regard as known. This has to do with representations of GLN, and they're twisted characters. So this is getting a little bit better. This right-hand side is to be regarded as something that we know, or at least that we want to relate the unknown things to. And then we have which I'll call 2 tilde, we have, and this is the thing that is not yet proved. This is under construction, I guess I said. This is the stabilization of the twisted trace formula of GLN. And so this would be I tilde n discrete of F tilde. And so that is, well, we work in the geometric side of things by Kottwitz and Schellstadt, and we certainly expect that it's going to be a similar sum. This time I'm going to write G to index the elliptic twisted endoscopic data for GLN. And so I'll write it down first and then just say a word about it. Again, some explicit coefficients, N, G, and stable distributions, this time attached to G, discrete, hat, F tilde of G. Okay, so I mentioned that this is Langland-Schellstadt transfer of functions from GA to G prime A. It's basically just a product of the local Langland-Schellstadt transfer at each of the completions. And again, this is Kottwitz-Schellstadt transfer from Gn tilde of A to G of A. So these endoscopic groups, this is G prime. I'll say just another word about the twisted endoscopic groups for GLN. They are also products, just like the ordinary endoscopic data for G are products. So if G is an orthogonal group, a group whose dual group is orthogonal, these are products of two smaller orthogonal groups. These are groups whose dual groups are orthogonal, smaller orthogonal groups whose product embeds in the usual way in the larger orthogonal group. Same thing with symplectic. This is the other way around. If G, the twisted endoscopic groups for GLN, the elliptic ones, are products of two groups, just like above here, except they are of opposite type. GS is a group whose dual group is symplectic. GO is a group whose dual group is orthogonal, and the product of those two things embeds in GL and C in the usual way that a conjugate of transpose inverse, its centralizer will be a product of an orthogonal group and a symplectic group. It's a little a little exercise in linear algebra that the natural twisted centralizers in GL and C are going to be, as complex groups, are going to be symplectic and orthogonal groups. So those are the dual groups. So G itself is a group whose product, whose dual group is a product of these two things. But they include the groups G that are whose dual group is purely symplectic or purely orthogonal. Okay, so what does this last thing represent? That's explicit. So these are the same stable distributions that come in up there. So finally, this is a relation. The fact that this is equal to this. This is something we know and we want to relate things to. It's equal to this thing, which is given as a linear combination of who knows what kind of stable distributions on the different groups G. But these stable distributions are the same as the stable distributions that occur in this formula, except, at least in the case when you don't have composite groups. Here you have a composite group where they're both orthogonal or both symplectic, and here you have a composite group where one's symplectic and one's orthogonal. But for the composite ones, whatever you're trying to prove, you assume inductively that you can do for the composite ones. And so what's left are the ones that are not composite there, and those represent the unknown things up there, which are related to the unknown things in the first formula that you want to understand. So That's what one wants to do. Now, to make the problem manageable, you fix a parameter. Let me write psi tilde of n for the set of global parameters for GLNC rather than parameters for G. Self-dual unitary representations, n-dimensional representations of this hypothetical Langlands group across SU2. So these things are, as I say, one can, what I'm about to write down, one can duplicate, but one has to prove some things in order to do it, in whatever we use to substitute for the global Langlands group. But these things are the same thing as the set of self-dual automorphic representations of GLNA, where these are irreducible, self-dual constituents of L2 of GL and F over GL and A. All right, the fact that these parameters correspond to these things bijectively, this is a sort of a famous theorem. This is a theorem of Möglen and Walsh-Burget. If the irreducible representations of the Langlands group itself correspond to cuspidal automorphic representations of GLN, then, which is what the premise that we're working under, then the representations of the product of these two things correspond to the discrete spectrum. The irreducible representations correspond to the discrete spectrum of GLNA. The fact that that is the case was in fact proved by Möglen and Walsh-Burget by analyzing the residues of Eisenstein series according to the general sort of non-explicit formulation of Langlands. Okay, that in turn, and this is a theorem of Hecke-Schleike, that in turn is bijective with a nicer set, a more concrete set, which I'm going to write as C tilde of n, the set of families of Hecke, of self-dual families of Hecke eigenvalues. I'm going to write that as C psi, C families consisting of families of semi-simple conjugacy classes for all but finitely many prime numbers. These are self-dual families of semi-simple conjugacy classes. In GLNC. I'm not saying that this is the set of all such families. I'm saying that the map that associates to an automorphic representation its Hecke eigenvalues at all unramified places, that completely characterizes the constituent of the spectrum, which follows from a theorem of Hecke and Schleike. So it's onto a set of such families, but a much simpler kind of object to deal with. And in particular, if you're given a function, a test function f, in any one of these four formulas, you can multiply f by, or you can multiply in the sense of, I guess, Fourier analysis. You can take a multiplier of f by something in the unramified Hecke algebra at all of the infinitely many unramified places. So you can fix f, and you can transform f by multiplying it. Well, multiplying it's Fourier transform by something in the unramified global Hecke algebra defined at almost all places. And then you can look at each of these formulas in that multiplier. And you're going to get a sum of eigenvalues of Hecke algebras, of this Hecke algebra. It's going to transform into a linear combination as a function of this multiplier linear combination of eigenvalues, simultaneous eigenvalues of these Hecke algebras. And so the contribution of any psi as an element in here can then be separated from all of the other contributions. So to make this more manageable, you can index the pieces of this thing by element psi, these parameters, or if you prefer the corresponding families of Hecke eigenvalues. Do I have 3 psis here? Yes, I'm going to call this formula 1 psi. I'm going to call this 2 psi. Call this formula 2 psi. Depends on psi in that sense. So you're taking the part of these, and this is 1 tilde of psi, I discrete psi of f tilde, mp psi, and ip psi, and same thing down here. This is 2 tilde of psi. Yes, yes.
I mean, I can see that if you have the Langland's formalism, I see you can sort of take the psi part, but we don't. And what you've really got is automorphic forms on these symplectic and orthogonal groups. And then you're trying to project them according to Hecke eigenvalues on GLN. Is it obvious that you can do that?
Yes. Again, I guess it's related to these maps being injective. If you have a parameter, a global parameter, it gives, so you have a global parameter, a map of, say, the Langland's group into the dual group of G. It has local embeddings of the local groups into it. Backtrack.
Sure. I mean, this is somehow a sum over traces of inductions of automorphic representations on orthogonal and symplectic groups. Let's look at formula 1. And now you want to somehow take the psi. Well, let's talk about 1.
Mm-hmm.
You want to somehow take the psi part of that.
Yes.
But psi is a set of eigenvalues of automorphic forms on GLN. How do you know everything?
So there is I didn't say it, there is a theorem here, or a lemma that, yeah, I think you're right. I mean, you really don't know that there might not be. How do you know that for an orthogonal or symplectic group, if this is your question, how do you know that there's not a Hecke eigenvalue, family of Hecke eigenvalues in these terms that has nothing to do with GLN? Is that what you're saying? Yes, yes. So that's basically the first part of the comparison that you have to prove. You have to prove that all of the Hecke eigenvalues that come in to this formula up there, say, for the classical group, all of them correspond to a family of Hecke eigenvalues for GLN.
Yeah.
In other words, the projection onto a family of Hecke eigenvalues of that first formula that has nothing to do with GLN, that it vanishes. That's what you have to prove. So that has to be proved. It's not.
I think maybe let me change this question. But you're going to take formula 1.
Yes.
It's a discrete plot of some trace.
Yes.
You're going to make the comparison by the other side of the formula, presumably.
Yes. No. The other side of the formulas are not part of this now at all. They've all.
Then I agree with you. Then how do you pull out the psi was something which anyway we don't know exists because it's not F, so we have to go to GLN.
Mm-hmm.
And everything's this black box of GLN and its form.
That's right. So any one of these formulas can be written as a direct sum of pieces indexed by eigenvalues of families of Hecke algebras.
For GLN?
Period. Yeah, I mean,
Hecke algebras possibly for the orthogonal symplectic.
That's right. That's right. Now they embed into GLN, so you can relate them to GLN. But what you don't know is, I think, if that's, I mean, Richard's question was, how do you know that there is not an eigenpiece of one of these formulas for G? Who's,
I'm more confused because I don't know when you're using a trace formula and when you're not.
so there's no, all I've got here are 4 formulas, but spectral sides of trace formulas. This is really a definition. This is a decomposition of the thing defined in 1 in terms of certain objects here that we don't know terribly much about. This is the same thing for GLN. So you have 4 formulas. And I am just saying that any one of these formulas, you can transform the given test function. You can multiply it by something in the unramified Hecke algebra at almost all places. You can break up the resulting thing as a linear combination of eigenfunctions of this, and then you can look at those components. Richard's question was, how do you know that for G, there's not a component that has nothing to do with? I mean, the Hecke GL embeds into GLN, so you can embed the Hecke eigenvalues for the classical group into GLN. But how do you know? Right. And so you prove you prove a comparison that you can't that there's that.
And that's going to come from the trace formula.
Yeah, right.
That comes yes, absolutely. Yeah, it comes from the identity of all these. No. It comes from these formulas.
It comes from those formulas.
So far there's just a
So those formulas without psi somehow imply that every psi that actually occurs.
Correct.
On GLN.
Yes. So the point is, Peter, that that there really is, once you add these 2 formulas to these 2 objects to the mix, there really is a robust formula. So what is, so just it's kind of, what your question basically leads to the next step. I mean, you have what you want to do, either with the psi or without the psi. What you want to do is to you've got so here's remarks on the proofs. So all of the theorems one would try to prove together by induction and by global methods. And the strategy, so I'll just write it out just to try to be clear. Try to describe. So what you want to do is to try to describe. So I hope I'll answer your question in the process of writing this down. You would try to describe the summand of M equal to G in 1 psi. That's the first formula. This is the unknown. That's the discrete spectrum of G. Okay, you want to describe that in terms of the summands of M in 1 tilde of psi. I'm going to leave those there. So this is a continuation of that sentence. You want to describe that through or from the chain. So you got a chain of 4 objects here. You've got 1 psi, 2 psi, 2 tilde psi, and 1 psi. Okay, so Peter, you agree that in the first formula, pardon me? Yeah, 1 tilde of psi, yes. So you agree that the term with M equals G in the first formula is what you want. What you know, at least from the point of view of the present exercise, is all of the terms in this formula. This is the discrete, this is the spectral of GLN. Agree? You're okay with that? So you want the term with m equal g up there, you want to describe it as an unknown in terms of these things, the known things, the spectrum of GLN. So you've got formulas that relate them. So there's a set of formulas that relate this, the unknown, to this. But it's passing through some murky lenses. You only get to relate this to this by passing through these two, right? I mean, because the second formula takes the unknown thing and it writes it as a bunch of stable distributions that you know nothing about. The third thing takes the thing that you know in terms of a bunch of stable distributions, but these are the same stable distributions that occur up there. So these things, there is a relation. This gives a relation between the unknown things up there. So there really is a chain of formulas to go from. So there's no geometric side at all now. That's all gone. That's what went into getting this equal to the thing up there, and this equal to this. So you want to relate this to this, looking through these rather murky lenses. So that's the overall strategy, and I'm just going to talk, maybe not without writing things down. Yes? I'll just... That's right. Okay, so what are the problems? So there's roadblocks. So maybe I'll answer. I'll see if maybe I'll answer the question. So that's the strategy. Here are the roadblocks, and I just tried to think of. I mean, I guess there's a number of them. I just tried to think of what sort of the roadblocks would be. First of all, these murky lenses that you have to look through before you get to this, they contain different kind of terms than the ones that you're hoping to find. These are stable distributions. These are stable characters, whereas those things up there are irreducible characters. So for a start, these are not quite the kind of objects that you would relate the first one to the last one. The fact that they're stable is what's responsible for making the representations occur in packets. But one could imagine that they do complicate. If you have to go through 2 psi, I don't want to get these numbers wrong. Yes, 2 are the stabilizations. So if you have to go through the stabilizations to get to where you want, you can see it's going to be a little complicated. Secondly, the term that you want up here is only the term, so that's the first kind of roadblock. Different objects, different kinds of qualitatively different objects in 2 psi and 2 tilde psi, namely stable distributions rather than stable characters, rather than things you want to relate to stable characters rather than irreducible characters. Moreover, there's extra terms even in the formulas that you've got. There are complications from extra terms. From extra terms, even in the first formula, you've got terms m not equal to g, and they're going to be part. They don't cancel out exactly the extra terms down here. They all get mashed together, and they all get, unfortunately, they all get plucked into mashed into the same formula. So those have to be somehow accounted for. You're going to have in 2 psi, you're going to have g1 prime, g2 prime composite. It's the ones where g is not equal to g prime is not equal to g prime is equal to g that will be the way you pass through 2 psi and 2 tilde psi, or g prime g equal gs cross go composite in the third formula. Okay, so those really represent extra terms that you don't want to have to deal with, but you have to deal with them because they are all you can't really separate out their contribution. Thirdly, you, in doing this, you also want to deduce the local theorems. So you want to deduce, must deduce. So by going through that, you've got to deduce the local theorems too. One and 4 from this. And perhaps most worries, I mean, I'm trying to make a story out of this. I mean, these have been dealt with, but I'm trying to sort of say it slightly dramatically. Most seriously is that this chain of equations appears to be undetermined. These equations are underdetermined. It looks like you do not have enough information in these equations to deduce the laws that you are trying to deduce. For example, n is even. Okay, so you're going to use the equation for GLN. Capital N is even. You're going to use these equations to try to get information up there about orthogonal and symplectic groups. Well, you have one equation for GLN when n is even, but you have two groups. You have two groups. GO hat is SO NC, and G symplectic hat is SP 2NC. And that's the only place you're going to be able to relate the stable distributions in one for these two groups. So you have one equation and two unknowns. So these equations appear to be underdetermined. And so that is actually a real problem. That is a problem that doesn't come up for unitary groups. The fact that you have only one twisted trace formula for GLN, and so out of that you somehow have to deduce the contributions from both the symplectic and orthogonal groups. All right, so just, by the way, the local, how does one deduce the local things? You basically specialize the test functions by letting them be of a particular nature at the places away from the local place you're trying to deduce it. And you also use the Archimedean case that you know because of the work of Shellstad, endoscopy for real groups. This theorem, by the way, much of the local theorems, in the case of the Archimedean case, has been proved by Shellstad, and I think perhaps all of it. It's conditional. I mean, it's conditional actually on all of that being proved by Shellstad, and it's under construction by Shellstad and Paul Mezzo. So you have to use the Archimedean what's known for Archimedean fields to deduce the local theorems from the global theorems. Okay, so that last remark was in the solutions. So that remark is how the solution for C. The solution for A, you basically have to find an explicit formula. Well, I won't go through, I won't say, you basically have to find an explicit formula for these stable distributions, and you have to prove it. You also have to find an explicit formula for these global intertwining operators as products of normalized local intertwining operators and special values of L functions and epsilon factors. You have to prove those formulas. And then for the second part, you have to basically find a combinatorial way to combine all of these things in sort of one large formula. And the last,
You say special values, which makes me nervous. It's just residues of those others, and is there also a special value at the central point?
No, I misspoke.
Just always residue.
No, neither of those things. It's not really special values. It's L of one. It's the kind of things that come in front of the constant term of Eisenstein series. L of zeta of S and zeta of, yeah, that's what I meant. And finally, let me just say, So this entails proving some sort of combinatorial identity, boiling all of the formulas into one combinatorial identity that contains all of these extraneous terms in such a way that you can analyze it. And finally, use, so that's B, find one large identity relating all terms. This was specializing F and F tilde and using Shellstead. And this was to analyze, use B to reduce the problem in C to the following lemma. Which is, suppose that you have a sum of non-negative numbers, C alpha, the lemma asserts that if you have a sum of non-negative numbers being equal to 0, then C alpha equals 0 for every alpha. So it's very lucky, actually. The fact that these equations look like they're overdetermined, when you sort them out, they're actually coefficients that all occur positively, and it happens about 4 or 5 times, and I don't quite understand the reason for it, but if that didn't happen, none of this would not be possible.
And positivity then is kind of critical.
Absolutely, yes.
So all these expressions are in fact the suitable channel.
Yes, you're right. Yes, the fact that those coefficients of Kottwitz, yeah, absolutely. Yeah, I should have thought of that. Yeah.
Wasn't the inclusion.
So anyway, that's just kind of a very rough idea of sort of what one has to try to do. So we can talk afterwards. We'll stop here.